Okay, so in this video, I'm just going to go over the PowerPoint lecture for the independent t-test and the paired t-test. There are already two separate videos that explain the paired t-test and the independent t-test quite extensively. Here, this video is just to go over the slides in case you'd like to read the slides and make sure that you understand everything in the slides. First off, I start in my slides with explaining that at the beginning of testing hypothesis, I focus on the one group. And so when you have one group and your outcome is numerical, so over here you have the outcome being numerical, therefore the hypothesis you're testing is that mu equals certain value. So mu equal 500, mu equal 1000, mu equal 3, depending upon the research question. And when you're doing that, you either use the one sample Z test or the one sample T test. The decision on whether using the Z or the T depends on whether you have sigma or not. On the other hand, if your outcome is categorical and therefore your null hypothesis is pi equal a certain fraction, so pi equals 0.8 or pi equals 0.5, in this instance, you're going to use the Z for single proportion, and we went over that formula in that lecture. And we also went over the requirement so that the the sampling distribution of either the mean or the proportion has to be normal to be able to use these two tests. Now, what comes next is an expansion of the testing hypothesis, whereby um, you have either two groups or you have three or more groups. So it's either one group, two groups, or three and more. But the outcome is still either numerical in nature, right here, or categorical in nature. Yani you're either interested in looking at averages, comparing averages, or comparing proportions. But the additional thing that is going to come into play here is whether the two groups are actually paired or not. If you're dealing with numerical data, and that's what we have been doing in the past two videos, and your groups are paired, you're going to be using the paired t-test. And the null hypothesis here is going to be mu of before equal mu of after, or mu of condition 1 equal mu of condition 2, or you can write it as mu of differences equal to 0. But if your two groups are independent, then your null hypothesis becomes mu of group 1 is equal to mu of group 2, and here you're going to use the independent t-test. So far we have covered the paired t-test and the independent t-test, and the lecture in this PowerPoint presentation is going to go over again the paired t-test and the independent t-test. In the coming lectures, we're going to expand the testing hypothesis, and we start looking at what happens if I'm interested in proportions, and therefore we're going to cover the Pearson chi-square and the McNamara chi-square. Again, the same idea, whether the two groups are paired or not. And then we're going to expand it further where you have three or more groups, and you'll be also testing if your outcome is numerical or non-numerical. Now, of note, once we cover the Pearson chi-square right here, this is the same test that we'll use even if you have three or more groups. So that will be covered right here once we do the this one right there. If the Cochrane Q is too complicated, and therefore we will not cover it in this course. And therefore what is left is the ANOVA, which is testing three or more groups with the outcome being numerical. And basically these are quite related. It's just a little bit of calculations that is going to allow you to move from here to here. And by doing so, we would have concluded the material for this course. All right, so let's move along looking at the paired t-test and the independent t-test. Again, as a reminder, I'm going to just go over the lecture because I already have two videos explaining what these are. Okay, so for the paired t-test, this is when you have two groups and they are matched. So for example, we want to look at diet in terms of people weight change. So you have the mu of people's weight before the diet and mu of people's weight after the diet. The alternative hypothesis is always not equal. Again, let me remind you here that the null hypothesis is written as something equals something. And since you're dealing with numerical data, then you're going to use the mu as your parameter. It's always a parameter in the null hypothesis and alternative hypothesis. So mu before equal mu after. Or you can write it as mu of weight change, and mu of weight differences is equal to 0, and the alternative hypothesis not equal to 0. So what I said that this looks exactly like if you're working with only one sample, but your interest is in the differences, and the null hypothesis is focusing on the differences being equal to 0. And therefore, your t-test that we used for the one sample, which was x bar minus mu over s divided by square root of n, applies. But we're not going to call it x bar, we're going to call it d bar, just for us to remember that we're dealing with differences, minus the mu of the differences, which, remember, according to the null hypothesis is going to be equal to 0, divided by the standard deviation of the differences, and that standard deviation of differences itself is divided by the square root of n of pair. And again, as a reminder, this piece down there, this is the standard error of the average differences. So here you have an example of 25 individual. You have their weight before the diet, you have their weight after the diet, and for every individual you can calculate the weight change, the weight difference, okay, for all of them. And therefore your x bar change, so this actually should be called your d bar, is minus 6 kilos. Yani on average, people are losing 6 kilos on this diet. The standard deviation for the change, yani for this column right there, not for before or after, just for the change, is 5.33. The degrees of freedom is 25 minus 1, and 24. Therefore, applying the formula, which is minus 6 divided by the 5.33 itself is divided by the square root of 25, will give you a t that is equal to minus 5.62. Okay, now I call it t calculated because I'm calculating this t. If you go to your t table for degrees of freedom 24, you're going to find that the p-value is less than 0.001. Again, as a reminder, p-value is the probability of t to be as extreme as negative 5.62, and as extreme as, since the t is negative, you're going to take this negative value and go down. If the t was positive, you will take the positive value and go up. But you also have to multiply by 2 to account for both sides of the distribution. So you look up negative 5.62, the table ما في negative value, so you have to do 1 minus t less than the positive value. Probably you're not going to find the 5, it's too big, and hence the largest area is 0.9995. 1 minus that area will give you 0.0005. You multiply it by 2, you get 0.001, but your p-value is still less than that. And we're going to reject the null hypothesis because, remember, usually your alpha is 5%. Obviously, your p-value is less than 5%. Okay, and therefore you're going to conclude that we have evidence to suggest that diet is making people lose weight. ليش lose weight مش gain weight؟ لأنه the average was negative here. And therefore we have evidence to suggest that it looks like this the diet is working. People are losing weight. Remember, when you reject the null hypothesis, you talk about statistical significance. So I can talk about that the weight change is statistically significant. I can say that. Whereas if I had failed to reject the null hypothesis, I would say that the observed difference in weight is due to chance only. So that's for that. Again, a reminder of what is a p-value. P-value is the probability of observing that much of a difference or more. And show the probability that we would have observed a difference in weight of minus 6 kilo or even more extreme than 6 kilo if in fact the diet did not work. Remember, that's step number 2, assuming the null is true. شو معناتها assuming the null is true? The null says there's no weight change and the diet doesn't work. So assuming that the null is true, the probability that you observe that much of a weight change or even more extreme is 0.0001, sorry, 0.001. which is quite unlikely to happen. Since it did happen, you're going to reject your null hypothesis. What is your null hypothesis? That the dye doesn't work, or there's no change in weight. So we're going to reject that null hypothesis, and therefore we're going to conclude that there is a change in weight, and the weight change is statistically significant. All right, so let's move on to the next slide. Thus, every time you have paired data, you can use the differences, the two time points, the two condition, or the case and the controls. And therefore, the test is reduced to just looking at the differences and as if you only have one group. For simplicity, and in this course, I do not look at case control matched. I only look at having the same person that is measured twice. Okay. All right. Now, since the test of two dependent sample is reduced to testing the hypothesis, then the number of pairs, n is the number of pairs, is not the number of before or after. You're only interested in one of them. If the number of pairs is less than 25, then to be able to assume that the sampling distribution of the differences is normal, you have to assume that the differences is normal. Or if the number of pairs is greater than or greater than or equal to 25, the central limit theorem applies. مثل ما قلنا the x and the x bar and the s are those of the differences. مشان هيك I call them d bar, and the test is called the pair t-test. Now, what if the two samples are independent? So, for example, here is the average weight of newborn boys different than the average weight of newborn girls. So, the null hypothesis is written mu of what? Weight of group 1 equal of mu weight of group 2. And then I have to specify which is group 1 and which is group 2. And the alternative hypothesis, mu boys is not equal to mu girls. Again, let me remind you that the null hypothesis is written something is equal to something. So you have the equal sign, the alternative hypothesis, ما في equal sign, and you have to use parameters here and parameters in the null hypothesis and the alternative hypothesis. Yani don't write x bar equal, it would be wrong. The other thing is you have to specify, meaning the two groups, and what is the measurement you're looking at when you're writing your null hypothesis. Okay, so the nature of the data is numeric. We are asking about the means. However, this time we are interested in two groups. They're not the same group. They are independent groups. So the steps that we follow are essentially identical to those that we followed for the one sample t-test. The major difference is the formula this time, and we're going to see how the differences. And also I'm making a note that when doing the pair t-test and the independent t-test, we do not work with the z anymore. We only work with the t because we do not assume that we have knowledge of the sigmas. All right, so again, here's your null and here's your alternative. You set alpha at usually 5%, as I said, but these values might appear in the literature. Don't be surprised. You need to calculate the test and you need to calculate the p-value. Then you compare the p-value to alpha, and therefore you state your statistical conclusion, and then you write your research conclusion. So here's an example right there. I don't know why I shifted to a different example instead of sticking with the newborn boys and girls. But what I have here is 15 men and 15 women, and I'm guessing I'm looking at maybe that's blood pressure. Yes, again, blood pressure. So the average blood pressure for men is 120. The average blood pressure is for women is 108. The standard deviation is 101, 10.1 for men and 10.5 for women. Notice that I have the same sample size per group, but I do not have to have the same sample size. Okay, so the research question, do men have an average blood pressure that is different than women? The null hypothesis is written as mu men equal mu women. The alternative hypothesis, they're not equal. Assume the null is true, set alpha at 5%. And now we calculate the formula. So as I did in the previous video, I have the t-test here. I split it into its component, the x bar, the mu, the s, and the 1 over square root of n. And I show you that the x bar is replaced by x bar 1 minus x bar 2. I show you that mu is replaced by mu 1 minus mu 2. The s is replaced by s pool, and the 1 over n square root is replaced by 1 over n1 plus 1 over n2 square root, all of that. Now remember, mu1 minus mu2 according to the null hypothesis is going to be equal to 0. And here I try to explain what is the S pool, which I kind of did that in the previous video. This is where your S1 and S2, both of them are trying to estimate the same parameter sigma. So you have two estimates trying to estimate one parameter, which is sigma. So instead of having two estimates, it's better to pull them together, to put them together to get only one estimate. The way you're going to pull them is you're going to calculate a weighted average. So S1 plus S2 divided by 2 is not a correct way to do it for multiple reasons. One of the reasons is that you may have different sample size, but it's good to remember that your S pool has to fall between S1 and S2. Okay, so how do we do that? You start from your standard deviation, S1, S2, you square them. So that becomes variance 1 and variance 2. You multiply by the degrees of freedom for each one of them. So that will give you standard deviation, sorry, sum of squared group 1, sum of squared group 2. You add the sum of squared together. So now you have total sum of squared. You divide by degrees of freedom 1 and degrees of freedom 2, which is your total degrees of freedom. And then you square root the total sum of square at total degrees of freedom, and that is going to give you the S pooled. Okay, so you're going to pool the sum of squares from each sample. You're going to divide them by the degrees of freedom for both, and you square root all of that to give you the S pool. So here's your formula of the S pool: S1 squared into N1 minus 1 plus S2 squared into N2 minus 1 over N1 plus N2 minus 2. You square root all of that, and you plug it into your formula of your independent t-test, which is right here. Remember, that piece is going to turn into a 0 in a second. And the degrees of freedom is N1 plus N2 minus 2. So going back to our example, the standard deviations came to 10.1 and 10.5. You square them, you multiply them by the degrees of freedom, 15 minus 1 and 15 minus 1 because you had the same sample size, and you divide by 15 plus 15 minus 2, you get a S pooled of 10.3. Okay, and quick notice that 10.3 is between 10.1 and 10.5. Okay, now someone might say, well, 10.3 is actually the average of 10.1 and 10.5. That works because your sample sizes were equal, but I think there is a fraction that is missing. So don't do S1 plus S2 over 2. It would be wrong. We go back to our formula. The formula says you take the average x bar 1 minus x bar 2, so 120 minus 108. You divide by the S pool 10.3. That is multiplied by 1 over 15 plus 1 over 15. So what you have down there is your standard error. So the difference is 12 divided by the standard error gets you 3.19. That is your t, your t calculated. Remember, to go from t to p-value, you need to calculate what is the probability of that t or as extreme as that t. Now, since this t is positive, meaning that your p-value is going to be t greater than or equal to 3.19, and you're going to multiply it by 2 for degrees of freedom, 28. You look up 3.19 for degrees of 28, you're not going to find it, but you're going to find 2.7633 and 3.64. Your t is in between, meaning that the probability of that is between the two areas. But notice what I did is I automatically took the 1 minus the two areas, and I also multiplied by 2 so that I get a p-value. And therefore, my p-value is between 0.01 and 0.001. Again, what is the p-value? It's the probability that the difference observed in blood pressure between men and women to be that much of a difference or even greater than that difference if in fact there was no difference between the two. Because remember, the p-value is calculated under the assumption that the null is true. What is the null? There's no difference in blood pressure, average blood pressure for men and women. So if in fact there was no difference in average blood pressure between men and women, the probability that I will observe a difference of 12 between men and women, or even more extreme than 12, would be between 1% and 1 per thousand. This probability is very small, very tiny, and therefore I would rather reject my null hypothesis, which is my statistical conclusion. And my research conclusion would be we have evidence that the average blood pressure of men is different than women. Now, different higher or different lower? Well, the data suggests that men have a higher blood pressure than women on average. I could have also said that the difference observed is statistically significant, because when you reject the null hypothesis, you can talk about statistical significance. When you fail to reject the null hypothesis, you say that the difference observed is due to chance only. All right, so what do we do? In research, what you have to do is you have to summarize your results. You remember this is the first part of this course. So you summarize your results by showing the table and your research conclusion. Here I have another example. Now I'm looking at BMI between normal weight and overweight in terms of, what is it, in terms of calcium intake, right? So I have two groups. I have normal weight BMI and overweight BMI, and I'm looking at the calcium intake. And notice that I have 21 individual in the first group, 16 individual in the second group. The average of calcium intake for the first group was 115. For the second group was 104. The standard deviations were 6.2 and 7.1. Again, the null hypothesis that mu for group 1 is equal to mu of group 2. Mu of what? Calcium intake. The alternative hypothesis, the mu, are different. We assume the null is true and we set alpha. Now here I set alpha at 1% just as a way to illustrate that this is a possibility. Next, you're going to calculate your t-test. To be able to calculate your t-test first, you have to calculate your S-pool. So you take the first standard deviation, you square it, and you multiply it by the degrees of freedom, plus the second standard deviation, you square it, you multiply it by the degrees of freedom, and then you divide all of that by the common degrees of freedom, يعني 21 plus 16 minus 2, and then you square all of this. You get 6.16. Sorry, 6.6. Notice 6.6 is between 6.2 and 7.1, so that it appears to be a correct answer. Then you calculate your t, which is going to be 115 minus 104, yani x bar 1 minus x bar 2, divided by the S pool, which is 6.6, we calculated there, and that is multiplied by 1 over 21 plus 1 over 16, so you get 5.02, and that's your t. For degrees of freedom, 35. Again, if you look at 5.02 for degrees of freedom 35, you're going to find that it's too big, and therefore your p-value is less than 0.0005 times 2, yani your p-value is less than 0.01, and therefore you're going to reject your null hypothesis. Once more, what is the definition of p-value? Let me go back a couple of slides. This is if in fact there was no difference in calcium intake between the normal weight and the overweight, the probability that I observe a difference of that much, 115 to 104, with this standard deviation, that probability is actually less than 1 per thousand, if in fact there was no difference in the populations. And therefore, I'm going to reject the null hypothesis that says that there is no difference, and I'm going to conclude that there is a difference where the average intake of calcium is not the same for these two groups. One of the two groups has a larger intake of calcium, and it's easy to figure that out by going to the data. You can see that normal weight consume more calcium than overweight individuals, and therefore I'm going to declare that the difference observed between these two groups is statistically significant. Again, if I failed to reject, I would have said that the difference observed is due to chance only. And like that, we have covered the lectures for the pair t-test and the independent t-test.